So let's look at this problem. Say we have, where'd you go? Sorry. The temperature at each point, x comma y comma z in space is given by t of x comma y comma z equal to 2x minus 6y plus 9z minus 5. Find the warmest point on the sphere x squared plus y squared plus z squared equal to 1. And we're going to use Lagrange multipliers. Although you could, no, it would be a mistake to do this a different way. So Lagrange multipliers, we have to set up the whole capital F thing, right? Capital F of x comma y comma z comma lambda is equal to, what is it equal to? Right, little f minus lambda times little t. And what's my little f here? I think that's actually my g. Oh no, you're right. No. Actually, I think you're right. I take it back. Let me, right? Yeah, right. We're on the sphere. We want to maximize the temperature. Right. Good. So that's our little f. So 2x minus 6y plus 9z minus 5 minus lambda times g, which is x squared plus y squared plus z squared. You don't really need the minus 1, but fine. And then we find all the partials. So fx is going to be 2 minus 2x lambda. Fy is going to be negative 6 minus 2y lambda. And fz is going to be 9 minus 2z lambda. And you could write down f lambda, but we've talked about how f lambda is just the constraint, so we don't really need to write that down again. Then we set these all equal to 0. And I feel like he does something funky. Like, I feel like he kind of brings one thing over to the other side and then like divides one equation by the other equation. Is that right? Okay. I mean, there's lots of ways you can do this. One way, so first let's rewrite. So I would write each of these as 2 equal to 2x lambda, negative 6 equal to 2y lambda, and 9 equal to 2z lambda. And I'll find one of the things his way and one of the things my way. So the way I would do this, I would solve each of these for lambda. So I'm going to say that 2 over 2x equals lambda and negative 6 over 2y equals lambda. And then set this equal to each other. So I'm going to simplify as well. 1 over x equals negative 3 over y, or y equals negative 3x. And then, so I use those two, then I'll use these other two. And I'll do these other two the way someone else might do them, where he likes to divide these equations by each other. So dividing these by each other, I'm going to get negative 6 over 9 equal to 2y lambda over 2z lambda. And the 2's and the lambdas cancel. And then you can say that, I guess I want to solve, so point of interest, right? Noticing here I have y equals negative 3x, and noticing here I have something with y's and z's. I want to write everything in terms of y, meaning I want x equals a function of y. So I really want x equal to negative 1/3 y. And I really want z as a function of y as well. So I'm going to have negative 6/9, which is negative 2/3 z equal to y. So z equals negative 3/2 y. And then we take each of those things and we plug them back into our constraint, and then we solve for whatever we want to solve, whatever we can solve for. So let's see. So I'm going to get, this is where things just get a little messy. I'm going to have negative 1/3 y squared plus y squared plus negative 3/2 y squared equal to 1. Then we solve for y. We're going to get two answers for y, because there's a warmest point on the sphere and there's also a coldest point on the sphere. So solving for y, okay, 1/9 y squared plus 1y squared plus 9/4 y squared. Who made up these numbers? Okay, So I've got, third, I guess I have to get a common denominator here. So 436 plus 36 plus 8136. Y squared equals 1. So y squared equals 1 divided by 40. Oh, that works out. Okay, that's kind of nice. 121 over 36. I guess someone was thinking about it when they made up these numbers. So that y is going to equal plus or minus 6 over 11. And then we can find x. So x and z will be the opposite side of y. So our points would either be, so x is negative 1/3 y. So x, if y was positive 6/11, x would be negative 2/11. Y would be positive 6/11. Z would be negative 3/2 times 6/11 is 18 over 22, 9 over 11. Sure, so negative 9 over 11. Or the opposite, 2/11, negative 6/11, positive 9/11. And then you plug each of these into the temperature thing to figure out which one gives you the max, the positive value essentially. And then looking at this, I can see the plugging in the second point is the one that's going to give me positive numbers. Yeah. So this is the answer. That's the warmest point on the sphere. Cool or not warm. Okay. So I know it's terrible. I couldn't help myself. What else should we do? That's kind of the only thing I really wanted to make sure I hit. Were there other topics that you feel like we should cover again?
Yeah, the final exam.
The final, yes, I do. Yeah, totally. There's lots. I mean, I feel like, I guess it's not that long. It feels kind of like a long exam to me, but I guess it's been a while since I took a 2-hour test. So what do I know? I guess it's not unreasonably long. Sure, where should we start?
First of all, how do you tell something's harmonic?
Oh, harmonic is a very specific series. So the harmonic series is specifically the sum from k equals 1 to infinity of 1 over k. That is the harmonic series. It's very famous.
Then, so in
17, well, there's a 17. Yeah, okay, cool. Yes, okay. Yep. It's the same thing. I'm just using k instead of n. So we could write this as the sum from k. So if I write out terms, this is the harmonic series 1 plus 1/2 plus 1/3 plus 1/4, which is the same as, I could just use a different index, which is what he's written there. He's writing it as the sum from n equals 1 to infinity of 1 over n. But it's still the same thing. That's going to be 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, all the way forever and ever and ever. Now, I wouldn't say this diverges because it's harmonic series specifically. Oh, I'm sorry, I heard B. I apologize. So I would just point out that instead of saying this diverges because of harmonic series, I would say this diverges because it fails, or diverges because of the P test. Right? Because RP is equal to 1. And if P is equal to 1, we get divergence. Sorry, but I heard B and you said E. Cool. So looking at E, so we have the sum from n equals 0 to infinity of n factorial over n plus 1 factorial. Okay, so let me ask. When we see factorials, what is our first thought as far as which test we should try? Always the ratio test. In fact, no other test really is going to work for factorials most of the time. So factorials automatically mean ratio test. So that's where we take the limit as n goes to infinity of the absolute value of the next term over the preceding term. So this, where we're thinking of this thing here, that is our a sub n. So we want to find a sub n plus 1. I'm just going to replace every n with n plus 1. So I'm going to write this as the absolute value of, let's see, so n, instead of n, I'm going to n plus 1 factorial. Instead of n plus 1, I'm going to get n plus 1 plus 1 factorial. And then I could divide by a sub n, but we usually try to skip that step and just multiply by the reciprocal of a sub n. So that's going to be n plus 1 factorial over n factorial. Okay, so let's see. I have a bad feeling about this. Sometimes that happens. So not that I'm right, I just have a bad feeling. So simplifying this, I see that n plus 1 factorial over n plus 2, so I should rewrite this. This is the limit as n goes to infinity of n plus 1 factorial or n plus 2 factorial times n plus 1 factorial over n factorial. And then we can simplify these. So how can we simplify n plus 1 factorial over n plus 2 factorial? Well, I always kind of think back to this. If you have a number factorial over one larger number factorial, you're going to get everything's going to cancel except for the one larger thing. So this is really just 6 times 5 times 4 times 3 times 2 times 1 over 7 times 6 times 5 times 4 times 3 times 2 times 1. And everything cancels except the 7. So this n plus 1 over n plus 1 factorial over n plus 2 factorial simplifies as 1 over n plus 2. And similarly, this n plus 1 factorial over n factorial simplifies as n plus 1 over 1. And this is disappointing because what's the limit of n plus 1 over n plus 2? Right? It is an infinity over infinity type, but what is the limit equal to? This is it. We know the answer here. Think back. So let me ask you a different question that will remind you that you know the answer. It is 1. Right? If I said what's the limit as x goes to infinity of 2x plus 5 over 3x plus 4. Right, it's 2/3 because the leading coefficients are coefficients of powers of x that are the same power, right? The degree is the same. So when the degree is the same, the limit is the fraction of those leading coefficients. But 1 is the one answer we don't want because that is inconclusive. So I will still say it's still right to have done the ratio test first, right? You see factorials, you should think ratio test. But if I was, I know what he did, but so what he did was he said, well, I should have just been smarter about this and rewritten this. So this is kind of a feint, right? They've thrown us a red herring here. We should have said, oh, I know that n factorial over n plus 1 factorial reduces to 1 over n plus 1. Well, let me ask you, were you okay with me reducing this here? Right? It's literally the same thing. But then look, this is again the harmonic series. If you start writing out the terms, if n equals 0, 1 over 0 plus 1 is 1. If n equals 1, 1 over 1 plus 1 is 1/2. And then plus 1/3, and then plus 1/4. Right, the harmonic series is the P series where the power is 1. And it always diverges. Well, see that what goes to infinity. Right, they do, but see, it's not super easy to see that right off the bat. For example, just as a counter example, what if I said what if I just did this? What if I would start adding up 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25? Do those converge or diverge? But it doesn't, right? So the thing is, that's why we have all these tests, because we don't really know just by looking at the terms right off the bat if they converge or diverge. But if we write this as the sum from n equals 1 to infinity of 1 over n squared, then we can say, oh, that's a P series, right? The sum from n equals 1 to infinity of 1 over n to the P. And here our P value is what? And if our P value is larger than 1, then we get convergence. So that's what's happening. That's the difference here, is that the power being 1 is kind of the tipping point between being convergent or being divergent. And that's actually, because we've talked about the limit comparison test, right? Yeah. So really you should, so whenever you see something that is just powers of n over powers of n, you should try to reduce it down to the highest power over the highest power. Meaning, if I had something like this, say the sum from n equals 1 to infinity of, what am I going to pick here? I don't know, something fun like n squared plus 5 over n to the fifth plus 3n plus 1. All that stuff that's not the highest power of n in the top or the bottom is just noise. The only thing we should really be paying attention here, and actually I'm gonna make this problem just slightly different. I'm gonna make this a 4n squared plus 5, or n to the fifth plus 3n plus 1. But all we should be paying attention to is the highest power of n in the top and the highest power of n in the bottom. So I'm going to say this is very similar to the sum from n equals 1 to infinity of n squared over n to the fifth. It's not direct comparison. Well, and I'll tell you why. Give me 1 sec though. I'm going to reduce this down to, well, let's see, n squared over n to the fifth reduces to 1 over n cubed. So to use either limit comparison, which is what we're going to use, or direct comparison, which is what we're not going to use, you have to know what the thing you're comparing it to does. So does the sum from n equals 1 to infinity of 1 over n cubed converge? Right. It converges because it's a p series where p is larger than 1. So this converges. So the thing over here, we are expecting it's also going to converge. Because right, exactly, because the top and the bottom are bigger, right? So I don't know, we can't just say that 4n squared plus 5 over n to the fifth plus 3n plus 1 is less than 1 over n cubed, because it's not. Right, exactly. Yeah, totally. Like if we were dealing with like n squared over n to the fifth plus 6, you could totally just do a direct comparison like that. And that would work out just fine. And you could say that that series converges because it's less than this a converse series. But here, since we can't just say it's strictly less than nothing all the time, what we're going to do instead is use the limit comparison test, which says you take the limit as n goes to infinity of the sequence for the unknown series on top. So the 4n squared plus 5 over n to the fifth plus 3n plus 1 divided by the known series sequence on the bottom. And then if this limit is, well, if you're looking for convergence, if this limit is either a finite number or 0, then they have the same behavior. If you're looking for divergence, you can have a finite number or infinity, but not 0. So here, and here's the thing that's always going to happen. For rational functions where you have just powers of n over powers of n, you're always going to get just some nice finite number, usually just whatever the leading coefficient is over here. So when we do this, we're going to get the limit as n goes to infinity. Well, if I flip and multiply, the n cubed times the 4n squared gives me a 4n to the fifth plus a 5n cubed over n to the fifth plus 3n plus 1. And just like before, when the limit was 1, same idea here. Powers are the same. So the limit here is going to be 4. And since that is not 0 and not infinity, both series have the same behavior. So both series converge because one of them we know converges. Good. So let's look at any of these other ones kind of funky. No, the other ones seem all right. Yeah.
I have a question
On 19? Sure. Take a look. Oh yeah, totally. Taylor polynomials. Right. What is the 6th? Ooh, fun time. Okay, sure. So what is the 6th degree Taylor polynomial of f of x equal to x plus 3 times sine of 2x around the center c equal to 0. Now there's 2 ways to do this problem. There's a right way and a wrong way. Or I should say there's a fast way and a long way. And he does not intend for you to do this the long way. The long way would be, just so you're aware, the long way would be to find the first through 6 derivatives. So you'd find f prime of x, f double prime of x, all the way down to the 6th derivative of x, which is going to be a pain. We're going to have to use the product rule over and over and over again. Things are going to get really messy. What's that? So yeah, but f of x is over here. I wasn't.
No, but I can't. read it.
Oh, I'm sorry. That is x plus 3 times sine of 2x. I apologize. Is it because there's a glare? Or is it because my writing is terrible? Either answer is fine. Okay, thank you. I need that feedback. I need to let me write it again. F of x is x plus 3 times sine of 2x. There we go. Much nicer. Okay. So yeah, so if you could find all the derivatives and then you would plug in all the centers, so you'd have like f prime of 0, f double prime of 0, etc. And then if you're doing this the long way, you would then say, okay, great, my Taylor polynomial is going to be the f prime of 0, sorry, f of 0, not f prime of 0, plus f prime of 0 over 1 factorial times x to the first, plus f double prime of 0 over 2 factorial times x squared, plus all the way to the sixth derivative evaluated as 0 over 6 factorial times x to the sixth. That's how you do it the long way. And sometimes you'll be given a function where it makes sense to do it that way because finding all the derivatives is really straightforward. Like if your function was just e to the x or just sine of x or even just sine of 2x, it would be reasonable to do it this longer way. But he's made it a big enough polynomial, right? He wants 6 terms or the 6-degree polynomial that you don't want to have to do this. And he's not expecting you to. So here's what the actual expectation is. There is probably an expectation. And I think on the front of this test, he gives you the expansions for sine, cosine, e to the x, and 1 plus x to the k. So there's certainly an expectation, if not just a straight up, he's giving it to you, that you know that sine of x is, I always like to think of it as all the odd powers, because it is. It's going to be x to the first over 1 factorial minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the 7th over 7 factorial. I don't even need the x to the 7th, right? Because I know that I'm going to stop before I get to that point. Right? Because if I want the 6th degree, my highest power should be the 6th power. They alternate. Same for sine and for cosine, all the terms alternate signs. So then I don't really need any of this. So then sine of 2x, I'm going to replace every x with a 2x. So sine of 2x is 2x minus 2x quantity cubed over 3 factorial is 6. And then 2x quantity to the fifth over 5 factorial is 120.
Why were you able to cross out the other one?
Because I know that since I want a 6th degree Taylor polynomial or a 6th degree polynomial, that the highest power of x should be what? Right. So I don't need an x to the 7th because x to the 7th times anything is going to be too high of a power. But I could write that out. So if I was actually, so like the next term would be minus 2x to the 7th over 7 factorial. Because this is what you actually usually do. You usually write the whole thing and then you just cross out the stuff you don't want. So then if I want x plus 3 times sine of 2x, well, that's going to be x plus 3 times all this stuff. 2x minus, I'm going to start simplifying this as well. 2x cubed over 6 is going to be 8x cubed over 6. And 2x quantity to the fifth over 120 is going to be 32x to the fifth over 120. And then I don't really need the rest of this.
So you just simplified.
Right, because 2 to the fifth is 32, 2 to the third is 8. So then we start multiplying things out, and I guess he did that too. Yeah, he did. Yeah, okay. So then we start multiplying it out, and I'll just point out that 8/6 is 4/3, and 32 over 120 is 16 over 60, which is 8 over 30, which is 4 over 15. So then if we start multiplying this out, I'm going to target my lowest powers of x first. So the lowest power of x I can get is going to be 3 times 2x. That's going to give me a 6x. And then the next one I'm going to get is going to be x squared, which I'll get by doing x times 2x, which is going to be 2x squared. So this problem is a nice problem in that you don't have any, how do I say this that way? There's no way to get x squared 2 different ways. So you're not having to like add up the coefficients from different things to get the actual term. So he's given you, like on this exam that was a kind thing for him to do. He could have made this a lot harder by having a lot of kind of interference between terms where then you have to kind of combine all the like terms. So something you might have to do under. So then we keep going here. Then I'm going to do 3 times this. So 3 times -4/3 is minus 4x cubed. And then x times this is going to be minus 4/3 times x to the 4th. And then 3 times this is going to be 3 times 4/15 is going to be 4/5 x to the 5th. And then x times this is going to be x times 4/15 times x to the 5th. So 4/15 x to the 6th. And we stop there because that is my 6th degree. Yeah.
There's no formula for this.
Well, I mean, he might. I don't know what he's giving you on your final. Okay, sure. So then, yeah. So what you do have to know, though, is you have to know that you can take sine of x and replace the x with 2x to get sine of 2x.
Just simplify this to you.
Right. Well, this to there, that to there.
And then further simplify.
Right. Just to be, and again, if I were doing this on the exam, I probably wouldn't have done that step, right? I probably would have just left it as whatever the number was. Like I would have left this as 2 cubed over 6 and 2 to the 5th over 120, and then just multiply things out and not simplified until I had time at the end, if I had time at the end. Again, I mean, it depends, right? Because like for me, it's easier to simplify and then multiply, right? Like I know that 2 to the 5th is 32 right off the bat, and I know how to reduce this really fast. It's easier to multiply small numbers times small numbers rather than small numbers times big numbers. So that's why I would simplify here.
Algebra kind of area.
A little bit, yeah. Should we look at 20? I think we should look at 20. What are the first 3 non-vanishing or non-zero terms of the binomial expansion? Binomial expansion, why would you say that? Okay. For f of x equal to 1 over 1 minus x squared plus 1 over 1 plus x squared. So again, we want to find the expansion. Oh God. What are you doing here? Like, what? I have no idea what he's doing here. I don't think we've talked about binomial expansion. Also, the weight. Well, no, it's a. I mean, okay, but why would you do it that way? This is a dumb way to do it. Here's how I would do this problem. I would recognize that we know that, and it's give. Oh, I guess he does give it. He does give this on the front page though. So I'll say he gives you that 1 plus x to the k, but you still shouldn't do it that way. It's stupid. Okay.
I don't even remember hearing the term binomial.
Right. So here's how I would approach this problem, because this problem is doable without using those words or that thing. We know that 1 over 1 minus x is what the sum of the geometric series x to the k is going to be. This is just 1 plus x squared plus x cubed, and so on and so on. Right, it's literally a geometric series, right, where your ratio is x. So it does have to be true that the absolute value of x is less than 1. That's the interval of convergence for this geometric series, this geometric power series. But then we can abuse this. We can say, great, well, then I also know that 1 over 1 minus anything is 1 plus whatever anything is, plus whatever anything is squared, plus whatever anything is cubed, and so on and so on and so on. So it's really just the sum from k equals 0 to infinity of whatever we have in that spot to the kth power. And so I can put an x squared there if I want to. Which means this is really the sum from k equals 0 to infinity of x to the 2k. But I could also put a negative x squared there and say that 1 over 1 plus x squared is really 1 over 1 minus negative x squared, which is going to be 1 plus negative x squared plus negative x squared squared plus negative x squared cubed. And so if I simplify these, so 1 over 1 minus x squared plus 1 over 1 plus x squared. So I'm just going to write the first few terms here. So I'm going to get 1 plus x squared plus x to the 4th plus x to the 6th plus x to the 8th plus 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th minus the next one. And then if I start adding these together, great, 1 plus 1 is 2. X squared minus x squared cancels. X to the 4th plus x to the 4th is 2x to the 4th. X to the 6th minus x to the 6th cancels. X to the 8th plus x to the 8th is 2x to the 8th. And those are the first three non-zero terms. So what I would say that this problem illustrates, at least from my perspective, is that if you have a 1 over 1 plus some other stuff, or minus some other stuff, you can always rewrite it in this sort of way where it's just the thing, 1 plus the thing squared, and so on and so on and so on. So to me, a better question might be, what's the Taylor expansion of f of x equal to, sure, x over 1 minus x squared centered at 0? And the reason I think this is a good question, or at least not an easy question, it may not be a good question, is because if you don't know how to approach this, you could spend forever doing it. Because you could say, well, I'm going to do this the long way and start taking derivatives. And that is usually, unless it's really made explicit, usually not the intention. The intention here is to use our knowledge. We know that 1 over 1 minus a thing is 1 plus the thing squared plus the thing cubed, and so on. Where in this case, the thing is that I want to get is x squared. I'm just trying to make it match what I've already got. So I might write this as, okay, 1 over 1 minus x squared is, I know I just wrote this before, but I'm going to write it again. It's fine. So we get the sum from k equals 0 to infinity of x to the 2k. But I'm not done, because I don't have what I've been asked for. I have 1 over 1 minus x squared, and they wanted x over 1 minus x squared. So what do? We just multiply by x. So x times 1 over 1 minus x squared, I'm literally just going to multiply x by every one of these. So I'm going to get x plus x cubed plus x to the 5th plus x to the 7th, and so on and so on and so on forever, which I can really just multiply this by x and get x to the 2k plus 1. And that would be the Taylor series expansion centered at 0 for this thing here. It's kind of cool.
I thought there's like some sort of formula in that development like add to the
Formula, but I would say usually the idea is to try to not use that formula. But here the formula is, yeah. So for f of x, the Taylor formula is f of whatever your center is plus f prime at your center plus f double prime at your center over 2 factorial times. Oops, I forgot. Oh gosh, I forgot a thing. Let me write it again. It's f prime of your center times x minus your center to the first plus f double prime of your center over 2 factorial times x minus your center squared. And it just keeps going this way. You do the next derivative at the center, you divide by the next factorial, you multiply by x minus c to the next power. That's your formula, which we often write as a summation as the sum from k equals 0 to infinity of the kth derivative at your center over k factorial times x minus your center to the kth power. But again, I'm trying my hardest to not use that formula unless I have to. Right. And the thing is really though, it's not so much, I mean, whether or not you memorize this, the hard part about this formula is you basically, if you're going to try and do it this way, you have to start taking all these derivatives. And unless the function is really nice and easy and has nice derivatives every time, it's usually going to get very messy. So if you start taking a first or second derivative and you start having to use the product rule or the quotient rule or the chain rule, it's a really good sign that you're probably doing it the wrong way. You're approaching, or not the wrong way, but the way that is not intended for you to do it. There is definitely a way to, an easier way to probably do that problem. There was one other thing. Oh yeah, I know what popped in mind. The other thing that I feel like he will probably ask you about when it comes to Taylor series is finding the radius of convergence for something. So for example, if we had, do I have a good example here? Maybe, yeah, cool, that's a great example. So let's say I had the sum from n equals 1 to infinity of -1 to the n plus 1 times x minus 5 to the n over 4 to the n times the square root of n plus 8. And I want to find the radius of convergence. So when you hear the words radius of convergence, you should think ratio test. That is always what we have to do to find radius of convergence. Technically, there's another thing you could do that we don't learn in this class, but as far as we're concerned in this class, you always find the radius of convergence by using the ratio test. So great, ratio test. We're going to the limit as n goes to infinity of, again, it's the an plus 1 over the an. Here we really actually do need the absolute values. So it's going to be the limit, n goes to infinity of -1 to the n plus 2 times x minus 5 to the n plus 1 over 4 to the n plus 1 times the square root of n plus 1 plus 8 is n plus 9. And then we multiply by the reciprocal of the nth term. So we're going to do a 4 to the n square root of n plus 8 over -1 to the n plus 1 times x minus 5 to the n. And then we group all the like things together. I would also point out that -1 to the n plus 2 divided by -1 to the n plus 1 is -1 to the something, it's -1 to the first, but in the absolute value, it doesn't actually matter. So I usually just don't even write it in the next term. So I'm going to write the limit as n goes to infinity of, I've got my x minus 5 to the n plus 1 over x minus 5 to the n. I've got a 4 to the n over 4 to the n plus 1. And I've got a square root of n plus 8 over a square root of n plus 9. You could probably skip this step, and if you're comfortable with skipping the step, and jump to the simplified step. The simplified step is I've got x minus 5. I've got 1 over 4. And I would rewrite the square root of n plus 8 over the square root of n plus 9 as the square root of n plus 8 over n plus 9. Because, and again, when you use the ratio test, powers of n, whether they're roots or squares or cubes or whatever, those parts always just end up contributing a 1 as a multiple, really. I was going to say nothing, but technically it's a nothing multiplicatively, which is a 1. Right, the limit of that is going to go to 1. For the same reason the other limits we did went to 1 or 4 or whatever they went to, because highest powers are the same and we get the quotient of the leading coefficient, and the square root of 1 is 1. So then we're left with absolute value of x minus 5 divided by 4. And we want that limit to be less than 1. Right, because the ratio test says that the series converges if the limit of this ratio is less than 1. So the thing is, we are trying to determine the value. Well, actually, we're not technically trying, but the idea is here to say, oh, well, if x was like 6 minus 5 over 4 is definitely less than 1. So this series would converge if x was equal to 6. It would converge if x was equal to 7. It would converge as x was equal to 7.3. Right? It would converge for all these values of x up to, well, the biggest x could be would be just below 9. Because if x were 9, 9 minus 5 is 4, and 4 over 4 is equal to 1. And when this limit is equal to 1, the test is inconclusive. But the whole idea is, right, ratio test. We want the limit to be less than 1 for convergence. If the limit is greater than 1, you get divergence. And if the limit is equal to 1, we don't know. inconclusive. So specifically for the radius of convergence, we say, okay, well, we're just going to take this limit and say it needs to be less than 1. And then we're going to say, okay, great. That means now now you can kind of see this last part whatever way you want. Basically, the coefficient of x is the reciprocal of the radius. So here, if I look at this, what is the coefficient of x? Well, it might help if I rewrite it as 1/4 x minus 5/4. What's the coefficient of x? What's the reciprocal of 1/4? Right. The radius is 4. But that's just the way I don't know. It's not the easy, it's just the way I've seen it for years. But really what I would probably do if I was like showing my work is I would multiply both sides by 4 and say great, x minus 5 in absolute value is less than 4. And then x minus 5 is between 4 and -4. So x is between 9 and +1. And then the distance from 9 to 1 is 8, and 8 divided by 2 is 4, and that's your radius. So the radius of convergence is 8 divided by 2, which is 4. But whatever, I don't know. I don't think he really cares what way you get to saying what the radius is, as long as you're able to identify it from this work. But basically, right, x can't be any bigger than 9, x can't be any less than 1. And so the diameter of convergence is 8, and the radius of convergence is half that. Cool. What else? What else seems important? I mean, it all seems important. What else seems like it might be on your exam? Important is hard to justify at the end of the last quarter of calculus, I feel like. Sure. Let's see what I've got here. I'm just trying to think about what other kinds of things we might talk about. Sure. You're fine. Yeah. Oh yeah, he does. Yeah. On the previous page, there was definitely an interval convergence problem. So I will point out in his solutions to his previous problems, right? He does it like this. So, interesting. He talked about he didn't actually state the radius of convergence. He found the interval of convergence, which I don't think is something you talked about in class, right? The interval of convergence. Just instead of saying how long the radius is, he specifically said where x has to live for it to be convergent. Yeah, it's they're very related to each other. But so what I would say is from here, once you've got x with a coefficient of 1, whatever number is over here is your radius. So here the radius of convergence would be 3. Just like for the problem we just did, once we isolated this and had a coefficient of 1, that number is our radius of convergence. See, yeah, the center would be 5. And you can see that because we have, I mean, but if you look at this series, we should be able to identify the center from the get-go, right? If you look at that, it's obvious to me that, oh yeah, of course x has to be 5 because 5 minus 5 is 0. Just like over here, it's obvious that x equals 4 is the center because 4 minus 4 is 0. Basically, whatever value of x you can pick, that when you plug it in, you get 0 there. That's your center. But also you can see that 4 is the center of 1 to 7. Just like here, 5 is the center of 1 to 9. Yeah, let's grab another question here. Okay, fine. So I don't love that, but I guess we do. So I guess we should do one example where we might actually have to use the formula, because he could actually ask you to use the formula. So let's say we want to apply Taylor's theorem, which is just using the formula, to find the first 4 terms of f of x equal to 1 over 4x minus 1, centered, this is a little trickier, centered at c equal to 1. And then write the general formula. So the idea, so then write the sum of whatever you've got times x minus 1 to the k. Right. So that's our plan here, is to actually write out the formula. You're doing it the long way. Now no, actually I won't say that, because that's not true here. I was going to say we could do this one the short way, but we can't, because the short way is for centered at c equals 0 and it's centered at c equals 1. So I'm just going to start doing the thing. So I'm going to start taking derivatives. And to do that, I'm going to first write this as something that's easier to take the derivative of. 4x minus 1 to the negative first. So then my first derivative here is going to be negative 1 times 4x minus 1 to the negative second times 4. And I would say if you're asked to do a problem like this, which I don't anticipate, but it could, it's usually in your interest to not simplify things if you're trying to see the pattern. So then my second derivative, f prime of x, not f prime of 1. My second derivative is going to be negative 2 times negative 1 times 4x minus 1 to the negative third times 4 times 4. Or 4 squared. I do think simplifying that's fine, because you can see that every time you're going to get another 4. My third derivative is looking like negative 3 times negative 2 times negative 1 times 4x minus 1 to the negative fourth times 4 to the third. And finally, my fourth derivative, I guess technically the way this is phrased, the first 4 terms would be using these 4 things. So I probably technically shouldn't find this one, but I'm going to do it anyway. Is going to be negative 4 times negative 3 times negative 2 times negative 1 times 4x minus 1 to the negative fifth times 4 to the fourth. So from here, I guess we could, then we should plug in 1. So f of 1 is going to be 3 to the negative first. And f prime of 1 is going to be negative 1 times 3 to the negative second times 4 to the first. And f double prime of 1. Now here's where I might start trying to see what things are doing. So I could simplify this as just 2, but what I really want you to see is that, so I don't want to say this is 2 and this is 6 and this is 24. I want to know what the pattern is. And when I think of having, if I ignore the negative signs, when I think of this as being 4 times 3 times 2 times 1, I really want to call that what? Right, 4 factorial. That's 3 times 2 times 1, that's 3 factorial. 2 times 1 is 2 factorial. 1 by itself is 1 factorial. And even a 1 there is 0 factorial. So this is exactly looking like I've got a 2 factorial times 3 to the negative third times 4 squared. And here my third derivative at 1 is going to be negative 3 factorial times 3 to the negative fourth times 4 cubed. And here my fourth derivative at 1 is going to be positive 4 factorial times 3 to the negative fifth times 4 to the fourth. So if I was trying to write the nth term of this, I probably could do it at this point. Because I can see that, well, I'll figure out the sign in a second here, but I can see that I'm going to have an n factorial. I'm going to have a 3 to the power that is negative, and that number is 1 larger than my n, so to the negative n plus 1, and I'm going to get a 4 to the nth power. And then I'm going to be alternating, so I'm going to have a negative 1 either to the n or to the n plus 1. I'm just going to check the first term. If it's n and I plug in 0, then I want it to be positive, which it will be, so that's good. So then to write out the formula here, I'm going to say it's going to be the sum from, I used k instead of n, oh well, from k equals 0 to infinity of this thing here, which is gross, n factorial, 3 to the negative n plus 1, 4 to the n, negative 1 to the n, over the n, fucking hell, sorry. I used n and I wrote k, gosh, fine, n, I should just stick with n. I know what I like, over n factorial times x minus 1 to the n. And then we should cancel the n factorials. So if I was writing this out, it would be the sum from n equals 0 to infinity of 3 to the negative n plus 1, 4 to the n. Well, I should be smarter about this, fine. It would have been smarter of me to combine the 4 to the n and negative 1 to the n as just negative 4 to the n. Oh well. I don't have anything to divide by, times x minus 1 to the n. And then if they actually wanted me to write out the first 4 terms, I would say, okay, the first 4 terms when I plug in n equals 0, well, I should really just look here, right? But I don't really want to do that, but fine. I'm going to get 3 to the negative 1, and then I'm going to get minus 3 to the negative 2 times 4 times x minus 1, and then plus, when I plug in n equals 2, 3 to the negative 3 times 4 squared times x minus 1 squared, and then minus, when I plug in n equals 3 to the negative 4th times 4 cubed times x minus 1 to the 3rd. Those would be the first 4 terms. Again, probably less likely to see something like this on your final, but not out of the question at all. It's a reasonable question to ask. It feels less likely, but not impossible. So
Wait, so if we don't use the formula, then you know exactly what
there is less of a short way for this problem. I could show you a short way, but I don't think it's going to be helpful. Well, so here's what I would say. If someone said, as a slightly different question, find the Taylor series for the same thing, 1 over 4x minus 1, centered at x equal to 0. It's sure, I'll show you. I don't think this is really super helpful though. But what I would do is I would factor out what would I do here? So what I'm usually trying to do is make it look like 1 over 1 minus something. Yeah, but that's fun. The problem is things. I guess I would rewrite. So I'd write 1 over 4x minus 1 as negative 1 over 1 minus 4x. And then this is looking like negative 1 over 1 minus, so this would be negative 1 over 1 minus my stuff. So then that's going to be negative 1 plus 4x plus 4x squared plus 4x cubed. So that's how you could do this centered at 0. But again, I feel like that's a little trickier than we would probably usually be asked. So that's the quote unquote shorter way you would do a problem like this. But again, it's not the same because it's centered at 1, not at 0, or this is centered at 0, not centered at 1. So when you're centering it somewhere that's atypical, usually it's much harder to kind of use this shortcut idea of just applying things we already know. Because most of the things we already know are usually centered at 0, right? Sine of x, cosine of x, e to the x, 1 over 1 plus x, those are all centered at 0. Or at least, it's just the way we typically write them, they're all centered at 0. They can all be centered other places, they just don't look as nice or as typical.